This is number 40 from the chapter review for chapter 2. So we have two balls, and we have a building. And the building is 15 meters high. We've got one ball that's being dropped from the top of the building, and another one being thrown up with an initial velocity. So the first thing you want to do with any problem like this, and we do a lot of these in the next chapter and in chapter 4, you've got two different objects. You actually want to kind of set up two different problems. So I'm going to do thrown and dropped, okay? Because we're comparing two objects in space and in time, but they really are kind of doing their own thing. So for the ball that's thrown, we have a VI, 25 meters per second. We have an acceleration. What is it? Negative 9.81 meters per second squared. We don't have a time. We don't have a final displacement. But we know we're looking for the point when these two things are at the same spot. So we know we're thinking about displacement. So we're going to end up needing delta y. Okay, I'm going to stick that in my list. The moment when they cross is the moment they're starting at the same time. They at that point have been traveling for the same amount of time. So delta t is really going to be the thing that connects these two motions. So that's all the things I can really list for my thrown object. For the dropped object, I have a VI. What is it? 0. That's really important. So I have an acceleration. It's the same as for the other one, negative 9.81 meters per second squared. And I'm thinking about where this object is in space, so I know I'm going to have to deal with its displacement. And I also know that delta t is going to be the thing that really kind of connects these two. In chapter 3, I talk a lot about delta t is the bridge, time is your bridge, because time is constant. Well, if I was looking for something that connected these four variables, and everything was on the table, I had no limitations, what would be my go-to expression? What would be the go-to equation for this? So I've got VIA, delta y, and delta t. What connects those four things? Not worrying about any limitations or what you have or how you have to solve it. Just what would be your choice of equation? Yeah. So in this case it's delta y, but yeah, delta y equals VI delta t plus 1/2 a delta t squared. And I skipped the delta there. I'll put it back in. Okay. Well, and you know what? For this side of the equation, that's not a problem, because our usual issue with using that for time is that we have to do a quadratic solve. But on this side, that's not an issue because VI is 0, so that goes away. So we now have an equation that on this side connects delta y, acceleration, and time. That's useful. Well, over here, if we try to do delta y equals VI delta t plus 1/2 a delta t squared, we run into that issue with the quadratic solve. But we still don't have anything for delta y, except that we do. We have a relationship for delta y. So leaving these alone for a moment, I'm going to jog my line over there. At the moment when these two things cross, what is true of their displacements? They won't be the same. Not necessarily. I mean, they might be, but we don't know that. So let's look at just that for a moment. So we have our dropped ball, we have our thrown ball. And this distance is 15 meters. So this one moves down some amount, and this one moves up some amount. And at the point when they cross, what is the sum of their displacements? 15 meters. So at the point when their paths cross, delta y throw plus delta y drop is equal to 15 meters. Which means suddenly we can solve for delta y in terms of just one of them. So I'll use the throw. So delta y throw is equal to 15 meters minus delta y drop. Okay. Well, suddenly, lo and behold, I have an expression that I can stick in here. And with that expression, I now have a means to solve this. Okay. Mm-hmm. Well, the building is 15 meters, yeah. I don't know if it's 15 or 15.0. It just says 15, 1.5. Okay. So if time is the bridge, you can create an expression for time. Because, oh, and don't forget, this is delta y of the dropped object, and this is delta y of the thrown object. Okay, so you now have an expression that you can create and work back in, and I will leave you with that for the overall tutorial as a challenge, and then I'm going to come help people who feel like they still need some help.